Hello and welcome to my presentation. My name is Jackson Scott and today I'm going to be talking to you about the research paper HoloPair, Securing Shared Augmented Reality Using Microsoft HoloLens. This presentation is 27 slides long and should take around 25 minutes, so let's get started. First, I would like to tell you a little bit about myself. In May of 2019, I received my Bachelor of Science in Computer Science with specialization in Machine Learning from Mississippi State University. Currently, I am a student at Georgia Tech, obtaining my Master of Science in Computer Science with specialization in Machine Learning. I also work full-time as a software engineer in the defense industry. The purpose of this presentation is to provide an overview of the research paper mentioned just a moment ago. I will provide you with background information on the paper, the problem presented in this paper, as well as the solution the researchers came up with to address that problem. Now, what should you walk away with? You should walk away with an understanding of what the researchers did and an understanding of the concepts they used to accomplish that. Now, I would like to acknowledge the researchers, and I will apologize in advance for any mispronunciations. The first two researchers are from the University of Oxford, Ivo Sluganovic and Ivan Martinovic. The last two researchers are from the University of Zagreb, Matej Srbek and Ante Durek. This was presented at the annual Computer Security Applications Conference in San Juan, Puerto Rico in 2017 on December 4th through the 8th. If you would like to read this research paper, the link is provided here as well as in the description of the video below. The agenda of what I would like to take you through today is first we'll talk about the background of the research paper, then we'll discuss the problem as well as the approach the researchers took to mitigate that problem. Then we will dive into the solution of that approach and go through four main sections of it. Finally, we will conclude. So let's get started on the background. What I would first like to present on is the concept of an augmented reality device. An augmented reality device is a device which continuously scans its environment in order to naturally overlay virtual objects onto the physical world. You may be familiar with the popular phone application Pokemon Go. This application makes use of complex computer algorithms to overlay the Pokemon onto the physical world as seen in the photo example. For the remainder of this presentation, augmented reality will be abbreviated as AR. In contrast to the virtual reality device, or in contrast to an augmented reality device, is a virtual reality device. The virtual reality device is a device that entirely replaces the physical view with a virtual one. The important distinction I would like for you to remember is that an augmented reality device, the user's view is not entirely virtual. Rather, it is augmented with virtual objects in the real world. The Microsoft HoloLens is a fantastic example of an augmented reality device. It is also the device we will be focusing on for the remainder of this presentation. Microsoft recently released this HoloLens, and its main innovation is that it has remarkably precise position tracking that does not rely on any sensors outside of what is built into the headset. The official platform for this is named the Windows Mixed Reality Platform, abbreviated WMR. Shared augmented reality is very important in this presentation. This is where multiple users are experiencing the same augmented reality environment using individual headsets. An important example of this is NASA, who is currently using the HoloLens as a tool for astronaut teams to experience walking on Mars. Now I would like to discuss three important features of the HoloLens that are important for understanding topics discussed later. The first feature is the ability for the HoloLens to spatially map and track an environment. On the HoloLens is something called the Holographic Processing Unit, or HPU. The HPU consists of two environment understanding cameras, a depth camera, an ambient light sensor, and a 2-megapixel video camera. All of these components work in tandem to create an immersive mixed reality experience in which the position of virtual objects is fixed in space with centimeter scale precision. A second feature is what is known as a world anchor, shared holographic experiences in which the same holograms are shown on multiple devices is at the core of many augmented reality experiences, as discussed on the previous slide. Microsoft's current toolkit, the Holo Toolkit Unity 12, provides supports for shared experiences via world anchors. A world anchor is when a specific location is broadcast by one headset to all other HoloLens devices in the area. That anchor is now used as a reference point in a shared coordinate system, in which the holographic objects for every user can now be accurately shared and dynamically located at the same position for all users. Lastly, there is the ability for the HoloLens to track gestures. Due to the lack of a traditional keyboard and mouse for input, the HoloLens relies on intuitive gesture control for feature navigation. Some of these commands are pointing and clicking, which is used for object selection or activation, zooming in a scene via a pulling motion, or a gesture called bloom, which is used for going back in a menu. Now let's look at the problem and the approach to that problem. The issue we're focusing on has to do with device pairing. Many of these shared AR experiences are both security and privacy critical, meaning that the data observed in the mixed reality environment must be protected and used only by those who are intended to do so. A common breach in shared experiences can be traced to when the AR headsets initially pair together. When two devices establish an initial connection, they are vulnerable to a potential man-in-the-middle attack. At the time of this paper, the Windows Mixed Reality platform lacked any official implementation of practical research towards securely pairing two or more AR headsets. Research into the secure pairing does pose some challenges, as previous research on device pairing, such as research into securely pairing a phone to a vehicle entertainment system, is not directly applicable. This centers around two specific obstacles. Firstly, instead of assuming a single user who controls two devices, AR pairing necessarily involves two users, each with their own device. It is also necessary to assume that the adversary can fully eavesdrop the out-of-band communication. The approach the researchers used to mitigate the man-in-the-middle vulnerability was to create a system named HoloPair. HoloPair is a software package that is both practical and usable for the secure pairing of two Microsoft HoloLens headsets. In order to test HoloPair, the researchers implemented a comprehensive user study. This study would evaluate the security guarantees, usability, and performance of HoloPair using 22 participants and a working prototype of the system loaded onto two HoloLens devices. The participants were separated into pairs and were tasked with using HoloPair to sync together HoloLens headsets multiple times. Of all the different pairings that the participants were asked to do, 20% of those trial pairings had simulated man-in-the-middle attacks. The participants were told there might be an attack, however, the attacks were selected and performed at random. This was done to eliminate bias and allow the participants an equal chance to mitigate the attack using the functionality of HoloPair. Let's move on to the system model. Here I will outline the scenario the researchers are using to study the effectiveness of HoloPair. The situation is as follows. Two users, user A and user B, are both wearing Microsoft HoloLens devices. They do not have a pre-shared secret, which could be used for verification. Both user A and user B want to securely connect their HoloLens devices to share an augmented reality experience. The headsets can communicate over a high bandwidth wireless channel, and they have no other direct means of communication. The users can communicate over an out-of-band audio or visual channel on which their headsets can independently and unobservably overlay content. The focus for the secure connection will be to utilize the visual channel instead of the audio channel. The visual channel does not depend on environment noise and is also significantly harder to inject into. The adversary, dubbed E, has the goal of using his or her devices to prevent the two users from establishing a secure connection. E can be co-located and be able to position himself or herself arbitrarily close to either user. E can eavesdrop on the visual channel but not interfere with it. This is because any intrusion on the visual channel would be detected as suspicious behavior by legitimate protocol participants. E cannot observe the independently generated holograms, and lastly, denial of service attacks are not considered. Notice down below there is a diagram depicting the two users in this situation. The design goals for the system model are going to focus on security, usability, and hardware requirements. That is, usability, the system must not require users to take their headsets off, as this is going to be normal in your typical working environment with an augmented reality headset. The system must be secure, and the system must also meet the hardware requirements of the AR headset. It must not be highly computational or memory intensive. Now let's discuss the solution to the HoloPair system. Let's discuss the pairing protocol. User A initiates the protocol by broadcasting the willingness to pair and distributing the public parameters of the underlying cryptographic functions, together with the location of the world anchor. Any other device that receives the broadcast will assume the role of user B as soon as their user confirms the willingness to pair. The next step in the pairing protocol would be that the public keys are exchanged. This would be where user A sends their public key to user B, who responds by sending their public key back over the wireless channel. After public keys are exchanged, a weak hash commitment step is taken. The human participants will be required to compare values generated from weak hash functions. This takes the form of user A commits to a specific instance of the weak hash, which is defined by a randomly chosen value k. That hash is then sent over to user B. After the hash commitment is received, the receipt of that hash commitment is acknowledged by user B over the visual channel. User A then opens his commitment by sending the encrypted value of k to user B. This encrypted message also includes the world anchor. After exchanging the value k, shared secret confirmation will take place. Both devices can now independently compute the weak hashes from the received public keys, which will be identical only if the exchanged keys are indeed authentic. The reason for user participation in the protocol is to confirm that the exchanged public keys are authentic, and consequently that the weak hashes independently computed from their values indeed match. By relying on the unique capabilities of augmented reality's headsets, the researchers increase the usability of the comparison by guiding users with holographic objects shown in the space between them, which are generated to uniquely encode the value of the weak hash values, which are computed in their headset. So a polygon will be constructed from the weak hash, and user B will be required to perform the specific gesture of the generated polygon, while user A confirms the gesture matches expectation. If user A concludes success, then user A will send the full hash to user B, who will then use that to confirm pairing success. On this slide, we have two images. The first image is of two users completing the shared secret confirmation step of the pairing protocol, in which user B will use a gesture to draw the polygon, and user A will confirm the accuracy of this action. The second photo is a diagram of the pairing protocol. Please feel free to pause this video and examine these two figures for a longer period of time. Now let's talk about the construction of the HoloPair system. The first parts, or the four parts I would like to discuss, are the network, the cryptographic functions, and the shared hologram via weak hash and the source code. The HoloPair system is constructed using Unity's high-level networking API, and that is used to discover that other devices are running the HoloPair prototype by broadcasting/listening to a specific message on a dedicated port. There is also no limitation on how far apart the two pairing devices are, i.e., you can connect through potentially different wireless networks. The cryptographic functions are used using Microsoft's implementation of the 2048-bit RSA, PKCS1 for asymmetric cryptography, and the 256-bit SHA-2 for hashing. The shared hologram via the weak hash is constructed by extracting bits from the base 64 string representation of the full hash. These bits were used to generate the n-coordinates that define the shapes. 10 different x-coordinates and 10 different y-coordinates were used. The source code is written in C# using the Unity framework, and the source code is available online at the link you see there. Now let's discuss the security analysis portion of the solution. The attacker succeeds if he or she is able to eavesdrop on the communication between A and B after the protocol execution. The researchers believe their protocol can be proven as secure with the examination of four premises. The first claim is that in order to successfully eavesdrop on the communication between user A and user B, the adversary must force the users to agree on a different set of public keys than they originally created. The attacker must do this without causing the protocol to abort. The second claim is that since the attacker cannot remain undetected, if he or she tries intruding in on the last step of the protocol, the attacker must ensure that the confirmation finishes successfully from both participants' point of view. This can happen only if the weak hashes are exactly equal and the polygons are exactly equal. The third claim is that even though the entropy of the weak hash is not large, the attacker will be required to commit some value k prime in step 2 of the protocol. The likelihood of choosing a k prime that results in exactly the right combination is inverse to the output space of the weak hash. The attacker has no other means than this for choosing a k prime. Lastly, the fourth claim is that even though the world anchor is sent over an insecure channel, any modification of that world anchor would only result in an abort of the pairing procedure. For if it were changed, then the two computed polygons would be out of sync and the users would realize this and then abort. Drawing a conclusion from these four premises, a man-in-the-middle attacker has no better option than to randomly guess a pair of replacement keys, and the likelihood that this will succeed is inversely proportional to the output space of the weak hash. We will now analyze the likelihood that a different pair of keys still results in a weak hash collision. The shape of each possible instance of the shared hologram is uniquely determined by its n-coordinate pairs. In our implementation, we use a total of 10 different values for both x sub I and x sub y, or x sub I and y sub I. And this results in a probability of another pair of keys resulting in the same shared hologram as the probability equals to 1 over n, or 1 over 100 to the nth power. Now, let's evaluate the experiment used in the solution. The experiment took the form of two separate sections, the pilot user study and the main user study. In the pilot user study, the researchers tested 3 different versions of the shared secret confirmation. 6 participants were chosen for the pilot user study, and all 6 of those participants actually preferred drawing the shape generated from the hash. Coincidentally, this method also has the highest amount of theoretical entropy of the 3 proposed solutions for verifying the shared secrets. In the main user study, there was a wider pool of candidates chosen. There were 22 participants. 14 of those were female and 18 of those were male. All of the participants were aged from 21 to 33, and none of the participants had prior augmented reality experience. For the setup of the main user study, all of the participants were invited to the study in pairs, solely based upon available time and no other criteria. Participants, upon arrival, were given the instructions and briefed on the entire situation. Participants were then told the goal would be to repeat the pairing process several times, during which an attack could take place. For the procedure of the main user study, each pair of participants was asked to perform a minimum of 10 pairing attempts. After the 10 attempts, the protocol roles would be switched, so user A would become user B and vice versa. During the procedure, 2 independent variables were measured. The attack simulation was one of them. So in order to simulate the user's ability to detect attacks, at random, 20% of the pairing attempts were maliciously attacked. And also, the other independent variable was n, the shape complexity. In order to evaluate the impact of complexity, in each pairing attempt n, the number of hash-shaped segments, was chosen from either 4, 6, or 8. The measured data of the procedure is as follows. Out of the 230 pairing attempts, 44 cases were ones with a man-in-the-middle attack. For each pairing attempt, 2 dependent variables were also measured: the timestamps in which the users entered each step of the pairing protocol and whether the pairing attempt was successful or a failure, either by correctly thwarting a man-in-the-middle attack or just pairing successfully under normal conditions. The results were as follows. The median pairing time for users was 8 to 9 seconds, with longer pairing times attributed to users who noticed an attack was in place. 91% of the simulated attacks were detected, so 43 out of the 47, and 98% of the pairing attempts were successful, 181 out of 186. Increasing n also, which would be increasing the number of shape segments, did not significantly affect pairing time. After the user study was completed, a usability questionnaire was used to determine the usability of HoloPair. This was taken in the form of the System Usability Scale Questionnaire. SUS is a reliable and general tool for evaluating the usability of various systems, which has been widely used since its introduction. A SUS score of at least 85 indicates that the reviewed system has an excellent usability factor. The participants' cumulative results gave HoloPair a score of 86.9. Lastly, the HoloPair computer performance is shown as below. You can pause here and examine the results further, but the main takeaway from this is that HoloPair has minimal impact on the computer resources available in the Microsoft HoloLens. Now let's move into the conclusion. In this paper, HoloPair was introduced, which is a protocol and a system for the secure and usable pairing of augmented reality headsets. HoloPair was tested using a prototype version on 2 Microsoft HoloLens headsets. A study with a total of 22 participants was run in order to evaluate the feasibility of the proposed protocol in terms of security guarantees, usability, and prototype performance. The results shows that users with no prior AR experience were able to achieve high rates of success at both pairing the headsets under normal conditions and detecting man-in-the-middle attacks when they occurred. The prototype has also been made fully open source and is available for download right now. It is also being put through the process of being added to the official Microsoft HoloLens development toolkit. And lastly, here are the SUS questions that were asked in case you wanted to view them. This concludes my presentation, and I thank you for viewing.